All right, 4.2 is going to have a discussion more on these idea of divisibility, and we're going to talk about prime and composite numbers. So to start with, we need to talk about what they are. So prime numbers are any positive number, any positive integer, with exactly two distinct positive divisors. So we explored this definition vaguely last time. So can you give me some numbers that are prime? 7 will work. Because, what are the factors of 7? 7 and 1. There's exactly 2 of them, right? And they include both the number and 1, and that's it. What else? 3. Same reason, right? 3 and 1 and nothing else. Give me one more. 19. I know that hurts some others too, but 19 will work, right? 19 times 1 is 19, and those are the only 2 factors. It doesn't break down any further. Composite. A number is considered composite, if it has more than 2 distinct factors. So can you give me an example of a composite number? 4. Because what are the factors of 4? Right, it has 1 and 4, just like the numbers above, but it also has a factor, an additional factor of 2. Okay, give me one more. 12. What are the factors for 12? It has a whole bunch, doesn't it? So it has the same 1 and 12 that we would have expected with prime numbers, but we actually end up with 2, 3, 4, and 6 as well. Okay, so those are composite numbers. There is a number that is neither prime nor composite. Well, 0 actually, I guess you could sort of categorize it that way. But I'm thinking about, what somebody said it, 1. The number 1. It just has one factor. Notice both of these definitions have this phrase. This says exactly 2 distinct divisors or factors. And this one says more than. So the question becomes, well, what happens if it has fewer than? And that would be the example of the number 1. The number 1 is neither prime nor composite because it doesn't fall into either of these definitions, does it? People feel awkward about that, but it really isn't. It's not prime. That's usually what people want it to be. They want it to be prime. It's not. 1 is not prime. Okay? All right, factorization is an expression of a number in factored form. So writing it as a broken down piece of 2 different numbers multiplied together. That's factorization. Now, when we look at prime factorization, that means looking at the factorization in terms of only prime numbers. So that's a little bit different. So if you looked at this one, for example, for factorization, we'll use the number 12 that you guys had before. We could write that 12 is 4 times 3. But that is not prime factorization. Why not? Because 4 isn't prime. So if we were using that same example and we wanted the prime factorization for it, I could take the number 4 and I could break it down into 2 times 2. And then I still have my times 3. And that would be the prime factorization of the number 12. There's a couple of things to notice here. Notice I don't put times 1 anywhere here, because 1 is not a prime factor. Okay, so it's not in the prime factorization notation. We never write the times 1. Okay, and you'll also notice, and I think it may come up later, is that this is unique. There is no other way to write the number 12 without these 3 prime factors. We could change the order, but there's no other different prime factors I could have chosen. It is a unique categorization. Okay? So taking a look at that, there are 2 ways that we can look at finding prime factorization. And I'm going to show them both to you. You may have seen both of them before. For sure you'll have seen at least one of them before. All right, so my number we're going to work with is 23,660. And I'm going to start with the one that's usually the one people have seen before. And it's called a factor tree. So I want to hear a show of hands. Who has seen factor trees before? And if you aren't sure, it's okay. You don't have to show me. Okay. So a factor tree takes the number and writes it on top, and then it breaks it down into any 2 factors of this number. So somebody looking at this number should be able to tell me at least one thing that this divides by. 10's a really nice number because it ends in a 0. So we know this is divisible by 10, like 10. Now 10's not prime, but it didn't have to be yet. We'll figure that out later. Now, if I take 23,660 and divide by 10, what is the other factor that goes with this? 2366. 2,366. If you have a prime number at this point, you stop on that branch of the tree. But in fact, both of these are composite numbers. So let's start with the number 10 and break it down. So what would 10 break down into? 2 and 5. And I am done with that branch of the tree because those two numbers are prime. That's how you know you're done. The numbers are prime. But 2366 I am not done with. What does it divide by? 2. I mean, we don't recognize maybe anything right off the bat, but we do know it's even, so it'll divide by 2, which is prime. 2366 divided by 2 is what? It's 1,000 what? 183. Good. Which is no longer even, so it's not going to divide by 2. So let's just kind of work our way up the chain of numbers. Is it divisible by 3? How did we test? You can add the numbers together. So if I add 1 plus 1 plus 8 plus 3, I actually get 13. That's a no-go. And I don't have to check any more even numbers, right? I don't need to check 4 or 6 or 8 because it wasn't divisible by 2. So I'm done with all my even numbers. I'm working with primes as well, if I could. So the next prime after 3 is the prime number of 5, which is no good, right? It doesn't end in a 5 or a 0. What's next? 7. Does it divide by 7? We don't have a rule for that one. What did you get, Alyssa?
169.
So it went into 7? Awesome. Okay, so this one actually is divisible by 7. And then we have a 169. Does anybody recognize what 169 is? That happens to be 13 squared. If you didn't recognize it, it wouldn't hurt anything. You just go up your list. We stopped at 7. The next prime number would be the number 11. And if you tested 11, it wouldn't work. After 11's 13, and then it will. So this one's 13 by 13. So the prime factorization is every piece that's on the end of one of the branches all put together. So when I ask for prime factorization, give me just a second, Marilee, we're going to identify that these are the prime numbers, but we need to actually write down the answer. So the answer is that I have 2 squared, because there's 2 2's. I'm just going to go in order, not that you have to, but 5 is next, so I'm going to write it next, times 5, times 1 7, so that's 7, and then times 13 squared, because there are 2 13's. Yes, Marilee?
I was just going to ask, how far should we go up to figure out a number is prime? Like if 1183 was prime? Like,
You're jumping the gun because I promise I'm going to get there.
Okay.
It's later in the lesson.
Okay.
Yeah. Yeah, to know whether it's prime, if you've stopped or not. Yeah, I'll show you. But give me just a minute, okay? All right, there's another way to do this. It's a little bit more organized. One of the drawbacks to prime factorization trees like this is that it's really easy as you're doing your factors to lose the end of a branch. I cannot tell you how many times I've graded work where everybody did the prime factorization tree right, but one or more people forgot one of the little pieces and they didn't circle it like I did my circles in red. Okay, so there's nothing wrong with this. You just have to be careful to make sure that your answer includes everything. So let me show you another method. And there's a couple of ways to do it. I'm going to do it in a, I'll do it the way that I normally do, which is in an upward fashion. We'll do it that way. I'm going to take the number 23660. Let me see if I did it that way. No, I did it downward. I'll do it this way. Your book probably does it this way. It's probably why. And we're going to divide. We're going to do our division. It's going to look like it's upside down. Okay? And we're going to identify the smallest prime number that works. What is the smallest prime number that divides this number? 2. So there is an order to what I'm doing, whereas over on the factor tree, you got to just do whatever you want. It's going to all filter out at the end. That's kind of nice, but this one has an actual ordering to it. So somebody divide 23660 by 2 for me and tell me what you get. I think that's what you get. Do you get 11,830? All right. And we do it again. We say, okay, smallest prime number that divides this, and we get the number 2. Okay, so you take 11,830 divided by 2. What do you get? 5,915. What's the smallest prime number that divides 5,915? It's a 5 this time, right? 2 doesn't work, it's not even. If you add the digits together, 3 won't work either. So what do you get when you divide this by 5? 1,183. You should be noticing we're seeing these numbers just like in the other method. Okay. So we know that's not divisible by 2 or 3 or 5 because we've already checked those. And it doesn't end in 5, so it's not going to be divisible by 5 again. So we would try 7, and you'd find out that 7 does work. What do you get when you divide this by 7? 169. At which point you can identify the 13 and the 13 just like we did before. The beauty of this is that the answer is right here. Okay, so the drawback is that it had this very structured approach, which means that I don't get to choose whatever order I'd like to do it in, and I might not particularly like a specific order. This is how I relate this to English. This is how I think about it. I remember when I was in English in elementary or in middle school, there was 2 different ways of brainstorming information. There was cluster diagrams, bubbles, things like that, and there were outlines. That's how I think about this. And it kind of just depends on how you think. I don't care which one you do. It doesn't matter to me whatsoever. But you should be aware of them because depending on what your students and how they think, one might appeal to them more than the other one. Okay? All right, this is a little bit different now because these numbers are not given in a whole number form. They're given sort of partially factored, right? So this partially factored form has sort of an odd feel to it. So could you multiply it all out and just go back and use one of your factor trees? Yeah, but you're going to be doing a lot more work than really was intended if you go that route. So these already have kind of a factored feel to them. If we take a look at where they are, we can simplify them from where they are instead of starting back at square one. All right, so if you take a look at 16 only, how does 16 factor? Do you remember? Or maybe we'll just do it. What does it factor down into? What divides 16? 2. Thank you, Kristen. 2. And then it becomes, what's next? 8. And then what's divisible? What divides the 8? Another 2 to give me a 4. And what divides the 4? A 2 and a 2. So as we're working with this, that 16 is actually 2 to the 4th. So this was 16 originally to the 4th. It's now 2 to the 4th to the 4th. I simply replace the 16 with the number 2 to the 4th. So everybody with me on that one? So I'm sort of doing these mini factorization steps. The next one's 81. We'll do a factor tree for this one because you probably are thinking it. What does 81 divide nicely into? 9 times 9. What do each of my 9s divide into? 3s. So 81 is actually the same as 3 to the 4th. But originally this was 81 to the 4th, right? So I've got 3 to the 4th, which came from the 81, and then I've got the other 4 because it was on the outside of the 81 to begin with, right here. Okay. How about 6? I'm not even going to bother to do a tree on that. What's 6? It's 2 times 3. And that's raised to the 6th power, right? We talked briefly about properties of exponents back in Chapter 3. We did a little foray into that briefly in about 3.4, I think. And we had some properties that allowed us to combine some things. For instance, when I have 2 to the 4th to the 4th, what do I do with those 2 4s? You multiply them. Good. So this is actually 2 to the 16th, right? And then we have 3 to the 4th to the 4th. We would also multiply them, so we get 3 to the 16th, right? What about the last one? This is 2 times 3 to the 6th. Good. That's 2 to the 6th and 3 to the 6th. Have one more property of exponents I'm going to be able to use, and I'm going to be able to use it twice. What is it? I add exponents by combining the ones that are the same, right? So here's my 2's. So this will actually be 2 to the 22nd. And then I have the 3's. So this will be 3 to the 22nd again. So this is my prime factorization. I don't know about you, but if you type in 2 to the 22nd and 3 to the 22nd, you might actually get a number your calculator can't handle. It's getting so large. It is going to be quite large. All right, so I'm going to stop on that one for now.